Hello everyone, let's continue with the fourth lesson of the Python web series of courses, which will mainly cover some Python basics. In this lesson, we'll introduce the concept of modules in Python, the object-oriented nature of the Python language, the concept of regular expressions, and how to handle date types. First, let's take a look at the concept of modules in Python. Why do we need modules? Modules allow us to stand on the shoulders of giants when programming. That is, we can use the work of predecessors to develop new functionality. A module is equivalent to an internal battery, ready to be used out of the box. We have already introduced that Python has the big advantage of having a wealth of third-party standard libraries. These standard libraries cover many functions, such as network communication, file processing, database interface, graphics system, XML data processing, and so on. These third-party standard libraries can be used directly by importing a module. Let's take a look at some of the third-party standard libraries. For example, the Pandas standard library is mainly used for data processing and analysis, and is also widely used in scientific computing in Python. NumPy is also used as a standard library for scientific computing. Beautiful Soup 4 is mainly used to process HTML documents, and we often use it in writing web crawlers in Python. Matplotlib is mainly used for plotting. Similar to the plotting function in MATLAB, we can use the Matplotlib library in Python to easily create exquisite graphics. Scikit-learn is an open-source machine learning module that is widely celebrated by people within the profession. TensorFlow is a deep learning framework. So is PyTorch. With these third-party libraries, we can easily write our own programs. For everyone to gain a more perceptual understanding of the Python module, let's look at it more practically. The loop branch structure, function definition, and data structures that we introduced earlier are the foundation and bottom layer of programming. In theory, we can use them to complete any work. But if we want to complete a huge software project and only use these tools, it's akin to build a skyscraper from the ground up, brick by brick, which will undoubtedly consume a lot of time and energy. However, we can speed up the process of our software development with the help of Python's rich third-party libraries. Well, let's now introduce Python's architecture. A Python program is a system of modules. It is a top-level file, which introduces multiple modules under it. This kind of architecture makes it convenient for us to decompose a large program into several program source codes via modules. Combine these source codes, we get a complete program. Python source code files end with a .py extension. A Python source file is usually called a module, and multiple modules can form a package. As you can see in the figure on the right, a Python program has this structure. First of all, we have a top-level entry Python file. This Python file calls the two modules B and C that we have written. Of course, the two modules B and C can also call each other. They can also call third-party standard module libraries. In this way, we will build a complete Python program. Let's look at the concept of Python packages. It is composed of several modules, Module 1, Module 2, and Module N. Each module contains some functions or some Python classes. Generally speaking, this is the programming structure of Python. Let's introduce the operating environment of the Python module. The figure on the right describes the inner workings within modules and the interaction between modules. This is the execution environment of the module. Let's take a look at what elements are contained in a module. First, the module may contain global variables, including some functions and some classes. The function may contain its own local variables. and the class may contain member variables and member methods. In the object-oriented programming section, we will introduce these concepts in further detail. The way to interact between the modules is using the import method, which allows for the access of elements inside the module. This is how modules operate. Let's take a look at how to import modules or how to reference any module. There are three main ways. Why would we need to reference another module within a module? This is because we want to access elements inside another module, including its variables, functions, classes, and so on. We build our own modules on top of the modules already written by others, which can improve the efficiency of our programming. The three ways of module import are import plus a module name, using the form keyword to introduce the elements. We can also import all the elements in a module by using the wildcard asterisk. But sometimes we don't need to import all the elements. When we only need to use some of them, we just import the element we need using the keyword from plus module name. There is a specific example on the right. We created a Python project of our own. In this project, we built two packages. One is package 1 and the other is package 2. In the root directory of the project, we have module 0. In package 1, we have module 1 and module 2, and in package 2, we have module 3. Let's take a look at how these modules can reference each other. We can reference module 1 in package 1 within module 0. The line of code we write to do so is import package 1.module 1. We also want to use module 3 of package 2. So we import package 2.module 3. This way we can import any element in module 1 and module 3 into the current execution environment. We can also import all the elements from module 1 of package 1 using the line package 1.module 1 import asterisk. Let's take a look at the specific differences in usage. We import module 1 in package 1 and rename it to M1. There is a test method in M1, which we can reference using m1.test. If we had used the package 1.module 1 import asterisk to import all the elements in module 1, the test method would also be included. We can then call the test method directly. Please pay attention to this difference. Above, we introduced the three methods of module import. Let's take a look at the usage of module import in detail. First, we import a module as a whole. If we want to import a third-part module such as NumPy, we directly import NumPy in the execution environment. When the program is executed, the Python interpreter will find the numpy.py file. It sits in a specific directory, usually under the site packages directory. We load all the elements in the numpy.py file, including its variables and functions, into the current execution environment. We can reference related elements in the module by adding a dot to the module name of NumPy. For example, NumPy is a standard function library for scientific computing, and it is a power function in it. We can use numpy.power to perform an exponential calculation. This is meant to perform the square operation on the integer 4, so the value it returns is 16. Sometimes the name of a module may be relatively long. If we need to reference it repeatedly in our environment, it becomes a bit cumbersome, because the entire name needs to be spelled out. We can then choose to rename the module using as a keyword. The specific syntax is import module underscore name as plus new name, usually a relatively short name. For example, we can rename the NumPy module to the abbreviate NP using the statement import NumPy as NP. In the current execution environment, we can now use NP to call a specific method, such as np.power. The result gets the same, 16. This is module renaming. Sometimes we may not need to introduce all the objects of a module into the current execution environment. We only need to introduce what we need. In this case, we use the syntax from plus the name of a module to import one of the elements. We can do this with not only methods, but also be variables or classes. In our previous case, we only needed to introduce the function of exponent. We would do that using from numpy import power. Then we no longer need to use numpy.power to call this function in the current execution environment, but just reference it directly as power and pass in the corresponding parameters. Sometimes we may need to reference multiple elements within a module. The syntax to do this is from module import element 1, element 2, and element 3. For example, we want to use the exponential operation, square operation, and maximum value operation in the NumPy module. Let's look at this specific case. We can use power directly. There is also sqrt, which is the root operation. It passes in a parameter 4, and the resulting root value is 2.0. The max function can find a maximum value of an element in a numeric data structure. Here we pass in a list. The maximum value it returns is 11. We've now learned how to import existing elements in a module by importing the entire module, importing one element in a module, and importing multiple elements in a module. Let's look at the search path of a module. What exactly happens when we import a module? First, the Python interpreter checks the module registry to see if the module has been imported previously. If it has been imported before, you only need to get the object of this module in memory, instead of reloading it from the file system. If you check the sys.modules object in memory and find the module that needs to be imported does not exist, it needs to then perform the following process. The first step is to create a new empty module object, which is in essence a dictionary, to facilitate the follow-up query. Then insert the module object in the sys.modules dictionary, load the corresponding element of the module object, and execute the module object code through the new module namespace. All variables pointed to by this code can then be referenced by the module object. This is the process of importing a module. What we need to pay attention to is that this process will only be executed the first time a module is called. After that, the module gets loaded into memory. When we import the same module again, we will skip the loading step and directly extract the loaded module object in memory. This is a more efficient design because we don't have to repeatedly load code from the file system, which includes code compilation, resulting in a very large time overhead. Thus, any program before running will search in memory to see if it hits the module. Let's take another look at the concept of module search path. We can load modules that have been stored by third parties, and users also need to be able to specify their own module path. The search path of Python modules executes in this order. First, the Python interpreter will check the currently running program and determine whether the module it needs to import is under its home directory path. If not, it will search for the module in the directory configured to Python path. Third, it will check the Python standard library directory. Lastly, it will check whether the user-defined file ending with .pth contains such a path. The 4 pods above constitute the path list in sys.path. This contains the actual configuration of the module search path in the Python runtime environment. We can view the above path by printing the built-in sys.path list. Specifically, we can use the Python interactive programming environment, import the sys module, and print the sys.path object. We will see the possible path of all modules in the current operating environment. The result looks like the following. The first and third are Python runtime environments. The second and fourth are user-defined path. This method allows users to add the directory of the source code they want to customize into the search path of the Python module. Let's take a look at how to view the current search path. We get the package path in the current Python runtime environment using the getSidePackages function. Programmers can add modules in their personal common directory to the module's search path. This allows us to provide a module that we wrote to other engineering projects. The way to do this is that the user needs to customize a file ending with .pth. In the file, add the path that you want to be retrieved by the Python runtime environment. For example, a directory such as opt data lookwork is added to the mypath.pth file. In the second step, we place the mypath.pth file in the side packages directory corresponding to the Python installation path. The Python interpreter will search for files ending with .pth in this path. If found, it will automatically add the directory configured in the file to the Python module search path list. In the third step, we look at whether the path was successfully added by the user. We still import the sys module in the Python interactive execution environment and print the corresponding path object. We see that the returned result already contains the search path of the user-defined module, which is the part indicated in the red box. This way, we can temporarily modify the module path in the Python module search path. Specifically, we write sys.path.append plus a specified search path. After the introduction, we return the list of paths, and we see that it has been added. This method allows us to not only configure in advance the modules in previous objects, but also configure a new module path during program execution. We've now introduced some basic concepts of Python modules and how they interact. Next, we explain Python object-oriented programming. Python is first of all an object-oriented programming language. Let's take a look at the advantages of object-oriented programming. First of all, it is easy to maintain. We adopt a structure designed with object-oriented thinking, and the readability is relatively high. Because of inheritance, even if the program requirements are changed, maintenance only needs to be performed on a local module. Thus, it is very convenient and low cost to maintain, which is a big plus. The second advantage is its high quality, because we can utilize existing modules that have been tested in previous objects. We can develop higher quality business functions on top. The third is high efficiency, because in software development, based on the needs of the design, we abstract objects in the real world into classes and use this method to solve problems. It is similar to how we think in our normal daily lives, so we can achieve higher efficiency and quality during software development. Fourth, it is easy to expand. Because it is object-oriented, it has the characteristics of inheritance, encapsulation, and polymorphism. We can actually design a system structure with high cohesion and low coupling, which makes the system more flexible and easier to expand. Moreover, the cost of iterative development is relatively low. Some basic concepts in object-oriented programming include classes, class variables, local variables, instances, methods, objects, and so on. These concepts are very important in object-oriented programming, and we will look at them one by one. First, we look at the concept of classes. A class is used to describe a collection of objects with the same properties and methods. Class is an abstraction of objective entities. For example, a student can be a class. The student class can then include many objects, such as student Zhang San, student Li Si, and so on. A class defines the properties and methods common to a collection of objects, and an object is an instance of the class. The properties of the class are presented in the form of variables. What are the class variables? Class variables are shared among all class instances. They're defined in the class and outside the function body. Class variables are usually not used as instance variables. For example, the student class can have a class variable, which is name, because we know every student will have a name, a grade, the courses he took, and so on. These can be class variables of a student class. Let's look at local variables again. Local variables are usually defined inside the method body and only operate within that scope. It will not be referenced by objects outside the method body. Another concept is instantiation. Instantiation is the process of creating an instance of a class, meaning that we instantiate the abstract concept of the class into a concrete object. Let me take the student class as an example. We can instantiate an object called Zhang San. His name is Zhang San. His age is 18. His grade is 6th grade, and so on. We then have an instantiated object. This is the concept of instantiation. Let's look at this again. Usually, the class will define some methods. These methods are shared by the instantiated objects. For example, in the student class, we can have a method to modify his name or write his grades and so on. The last concept is the concept of objects. In the process of instantiation, we create an object. An object is a special case of a class, which contains its corresponding member variables and data structures, all filed with specific values. This will form an instantiated object. These abstract concepts we've introduced may still be difficult to understand, but we will have some specific examples later. We first look at the concept of objects and classes. Objects are the core of object-oriented programming. We usually abstract things that are similar or identical. After abstraction, we will get the concept of a class. And this cognitive process is the core logical process in object-oriented programming. Usually, the class will contain some attributes and behaviors. For example, if we define a class like person, what attributes would it have? He has gender, his blood type, name, height, weight, nationality, and so on. What do people do? He can walk, run, eat, drink, study, work, talk, etc. These are not specific to an individual, but to people as a type, which share these attributes and behaviors. In another example, for a class like vehicle, what attributes does it usually have? It has its type, size, price, and so on. What are its behaviors? It can be started, it can go backward, or it can go forward, etc. For a class like dog, it may have a name as well as some attributes such as color, weight, and species. What are its behaviors? It can run, it can wag its tail, it can bark, etc. Through these three examples, we can see that we are able to basically abstract anything in the objective world as an object-oriented class, as long as we can extract common attributes and behaviors. Let's look at the process of instantiation below. Take the social network information dataset of American high school students as an example. All high school students form the class. There are many attributes in the class, such as name, age, gender, grades, and so on. We can operate on these attributes, such as changing their name, comparing the age of two high school students, raising or lowering their scores, and so on. These operations are called methods, and these attributes and methods are combined and wrapped to form a class. That is, we have defined a class for high school students, which include some attributes and methods. Then we look at the process of instantiation. Two objects of high school students are instantiated on the left and right. We look at the object on the left. We call him student 1. What attributes does he have? His name is Zhang Fang. His age is 16 and his gender is male. His grade is 2 and his score is 4.3. Now we look at the instantiated object on the right. She's high school student 2. Her name is Wang Mei. Her gender is female. Her age is 17. Her grade is 2. And her score is 3.5. Through this method of instantiation, we get two objects of high school students. We can see that a class is an abstraction of concrete entities, and these entities are the objects. It is a back and forth process. We abstract concrete entities in the objective world in classes. then instantiate them into a concrete object of the objective world. Let's take a look at the definition of a class. We briefly explained the concept of class and its logical intuition. Now let's take a look at how we define a class in the Python programming language. First of all, Python has a keyword called class. All of our class definitions start with the class keyword, followed by the name of the class. Use a colon to indicate the beginning of a class definition. After the class header is defined, we can write many corresponding class elements, including class member variables and member methods, within the class. For example, we define a simple class that contains a member variable and a member method. We first start with the class keyword and give the class a name. Starting with a colon opens a new namespace. At this moment, we can define a member variable with the value 1080 and a simple method that returns a string hello world. We've now defined a simple Python class. Even though it doesn't have much functionality, it allows us to see what elements a class can contain. It is also worth noting that in naming classes, we usually start with a capital letter. For other elements, just to conform the naming convention of identifiers. How do we use a class after we've defined it? We must first instantiate a class object. The following 3 lines of code represent this process. In the first line of code, we instantiate a simple class mySimpleClass and get an instantiated object named mySimpleClass. We can see the name of the object is not the same as the name of the class. We call a method in the class through the object, which is the func method we've defined. The method returns a string which is assigned to the variable string. We then print a string. We see that we can utilize a class by first creating or instantiating an object of the class, and then we're calling the elements of the class from the object. Now we can start to define a meaningful class. That is the class person. Earlier we also talked about person, which has some attributes and behaviors. Let's take a look at how to express it in Python. First of all, start with the keyword class. The name of the class is person, and we start the definition of the class with the colon. We define an initialization method called a _init_. The init method is an initialization method, and several parameters are passed in. These parameters express person-related attributes, including his name, gender, age, height, weight, and so on. We can assign specific values to these initialized variables using passed-in parameters. We also define 2 methods. One is a speaking method, and the other is the eating method. Each method passes in its own parameters. There will be a specific method body inside the method. We have now completed the definition of the person class, including several attributes and methods. Let's take a look at how we can create an instance of the class we just defined. The process is like this. We will first call the initialization method of the class, pass in the corresponding parameters, and return the instantiated object to a variable, which is also the name of the object. How do we then access the properties in the object? We can now reference the height attribute through the object Tom. When we print the attribute, we will get 180 centimeters, since that's the value we've passed in. Then let's look at how to call a method of an object. For example, we want to call the eating method and pass it a parameter foods, which is a list of the names of the food he ate. By calling this method, we will get the eating string in return, containing these specific value of eating_foods. When they try to print it out, this is how we can reference the attributes and methods of an object. We need to also look at a special method called the init method. The init method is called the constructor of the class, or the initialization method. That is, when we create an instance of a class, we usually call the init method to complete the instantiation process by passing in the requisite parameters. We are simply assigning values to the member attributes of the object. It should be noted that the first parameter self in this method represents the class instance itself. When passing in parameters, We don't need to do so for this position, as it will be automatically ignored by the Python interpreter. For example, when we create an object of the person class, the parameters we pass in start from name and bypass the self parameter. Let's take a look how to correctly create an instance of a class. Now we will illustrate 3 ways that will result in errors when creating an object. In the first case, we directly call the person class to create its object and assign it to Tom. But during the creation process, we do not pass any parameters to the class. An error would be reported stating that we must pass in 5 parameters, what we have passed in on. This is easy to understand. When we instantiate an abstract class into an object and don't pass in any parameters, the object we instantiated cannot become the concrete instance. The second type of error is that the number of parameters we passed in is not sufficient. We originally needed to pass in 5 parameters, but in fact, we only passed in the name, gender, and age, and not height and weight. It will report an error clearly stating that there are 2 missing parameters, height and weight. The third error is that we mentioned before that there are 3 ways to pass parameters to a method, including by position, by keyword, and in a mixed form. We know that if we want to use the hybrid approach, the keyword parameter must come after the positional parameter. In other words, if the first parameter name equal to Tom is passed in by keyword, and the following 4 parameters not by keyword, it will report an error stating that the positional parameter must come before the keyword parameter. When we use a keyword parameter in any position, all subsequent parameters must also be keyword. If we just avoid these 3 cases, we can easily create a class instance. Now let's take a look at the 3 main features of object-oriented programming: encapsulation, inheritance, and polymorphism. What is encapsulation? The process of encapsulation is turning objective entities into abstract classes, whose data and methods can only be operated on by other trusted classes or objects. That is, the class has a visibility range, and information is hidden from untrusted entities. Encapsulation is one of the characteristics of object-oriented programming, and it is a key feature of objects and classes. Simply put, a class is a logical entity that encapsulates data and the code that manipulates the data. Some code or data within an object can be private and cannot be accessed by the outside world. In this way, the internal data of the object provides different levels of protection to prevent accidental changes or errors in irrelevant parts of the program. Having certain elements privatized is essentially the concept of encapsulation. Now let's look at inheritance. Inheritance means that an object of a certain type can acquire the properties of an object of another type. This means that we can have a parent class and a child class that embodies this relationship. For example, our parent class can be animal and our child class mammal. Mammals have all the characteristics of reptiles, but also have some of their own characteristics. In this way, we have realized the inheritance relationship. We can easily inherit some methods and properties of the parent class and add other unique ones to the subclass. When doing so, the logic structure is relatively clear, and it can reduce the amount of coding. Finally, we'll look at polymorphism. Polymorphism means that the same method of a class instance can actually behave differently. For example, the polymorphism mechanism allows objects with different internal structures to share the same external interface. This means that although the specific operations for different objects vary, these operations can be invoked in the same way through a common class. Below, we will explain these 3 abstract concepts using examples. The encapsulation feature of the class is to protect the member variables and methods inside the class to a certain extent. But in some instances, even if the data is encapsulated in the class, the programmer can still access them externally and change their values. At this time, encapsulation has been broken. Let's give an example. We define the person class and instantiate an object. For the instantiated object Tom, we print the height. We know that for the height attribute, we have assigned it a value of 180 centimeters, and the value it prints should be 180 centimeters. Outside the class, we can reassign height to 185 centimeters, and we would get 185 centimeters when printing. At this time, we will say that there is no effective encapsulation of the height attribute in the person class because it is easy to modify after instantiation. We know that encapsulation is meant to privatize member variables and functions because we don't want certain them to be accessed externally. To achieve this, we have to add 2 underscores in front of the attribute name to indicate that this is private. Now we define the simple person class with only 3 attributes: name, gender, and age. We indicate that these 3 attributes are all private member variables by adding 2 underscores in front of their names. These member variables can now be accessed inside the class but not outside. Let's see how this works in practice. For the simple person class, we instantiate an object called person underscore A, and the 3 parameters passed in are Tom, male, and 18. Now we try to directly access methods and a member variable of the object from the outside of the class using name of object dot name of member variable. But we get an error. The error states that the simple person class has no underscore name attribute. This is because we have defined the variable as private, and we cannot directly access the value outside the class. But do we have a way to bypass this? The privatization of member variables does not mean that they cannot be accessed from the outside at all, but it does raise the threshold of access. This is to prevent external changes to variable values which can cause some uncontrollable errors. But it doesn't mean that they are completely inaccessible. How can we access them? We simply add an underscore before the name of the class in the calling statement. Now we can have external access to private member variables. At this time, if we print the corresponding member variable and it returns the value Tom, similarly, when we print age, we get 18. Above, we introduced the privatization of member variables. Can we also privatize the class functions? In fact, it is also possible. Encapsulation allows for not only the privatization of member variables, but also that of member functions. We do so by again adding 2 underscores in front of the function name to indicate that the function belongs to the class. Now this function can only be accessed inside the class and not outside. As we learned before, if we want to access them from outside of the class, we will need to add the name of the class with an underscore in front of it. Through this splicing, we can access the private member function underscore speaking in the simple person class. In our example, content is equal to I like this book. Call this method and we get the result. The speaking content is I like this book. Now let's talk about inheritance. The child class can inherit the member variables and member functions contained in the parent class. Class inheritance behaves just like in real life. Children have many characteristics of their parents. In programming terms, if a new class inherits another class, the new class is called a subclass, and the class inherited by the subclass is called the parent class. For example, for a class like person, it is the parent class. We can have both the student class and the teacher class as subclasses. These 2 figures illustrate this relationship. For the student class and the teacher class, we did not define their own unique member attributes and methods. Let's take a look at a specific example. We allow subclasses student and teacher to inherit parent class person. We can simultaneously inherit the attributes and methods of all parent member classes. Say we define the student class using this syntax. It passes in a parameter that is the name of the parent class person. We then create an instance of student and print one of its attributes. We see that its value is Tom. indicating that the child class student has inherited all the member variables of the parent class person. It also inherits the speaking method, which means we can get the corresponding return value. Let's look at another feature. If the subclass defines a function with the same name as that in the parent class, which function will the instantiated object of the subclass execute? There is a specific concept in object-oriented programming called function overloading. What is the actual result? The execution of the method defined in the subclass will be given higher priority. We can see in the example. The person class has a speaking function and the student class inherits the person class. And we again define the same function in the subclass with a different code block. We then create an instance of student and call the speaking method with the instantiated object. We can see that in fact, it executes the overloaded method body in the student subclass. This is the process of a subclass overloading the functions of the parent class. We have now covered some basic concepts of object-oriented programming and will move on to some related concepts of regular expressions in Python. Let's begin. Before introducing why we need regular expressions, let's take a look at wildcards. There are two main wildcards in Linux. One is an asterisk and the other is a question mark. The asterisk can be used to match any number of characters, while the question mark can match any singular character. Let's look at two examples. First, we use the asterisk wildcard to list all Python files in the current directory. In the Linux shell interface, we can enter a command like ll**py to list all the files ending in .py in the current directory. Here we can see that the asterisk can match any number of characters. Looking at the second example, we use the question mark wildcard to accomplish the same task. Since the question mark can only match one character, the syntax we use becomes **y, yielding the same result. This is the difference between an asterisk and a question mark. But because there are only two types of wildcards, they often don't grant sufficient flexibility, or we can see that they are not expressive enough. We've now seen the function of wildcards. Let's talk about why we need regular expressions. Regular expressions allow us to extract information that conforms to a certain pattern from unstructured strings. Just now we saw that wildcards have a certain expressive power for strings, but they are not sufficient. Regular expressions are a more powerful way of expressing patterns. Let's continue below. Within an ordinary string, we can use wildcards to construct a new expression pattern. For example, what we mean by A**B is that between A and B can contain any singular character, while A**B means that between A and B can contain any number of characters. This way we can create a number of string expression patterns. But we said that wildcards are not flexible enough, and their descriptive ability is not strong enough, so we have to introduce regular expressions. Regular expression is a very meaningful and practical pattern language. It can achieve more flexible, more specific, and more powerful functions. Let's look at an example. In the lower right corner, on the left is a collection of strings. We can see that the collection can be expressed using wildcards as p, parentheses, yh**. What does this represent? It is a string that starts with the letter P and it contains any number of ensuing YH, but could be none. This results in a set of strings on the left. We've now seen how a simple regular expression pattern can represent a collection of strings. Now we give a more standardized definition of regular expressions. What is a regular expression? A regular expression is a universal string expression framework, and different programming languages encapsulate their own regular expression modules. For Java, it is the util.regex package. For Python, it is the RE library. Of course, our follow-up content mainly introduces the Python regular expression package. Let's take a look at some syntactical rules of regular expressions and some of the basic concepts involved. Regular expressions contain several types of characters, and we need to understand and distinguish between them. What are they? The four main types are ordinary characters, non-printing characters, special characters, and qualified characters. Let's first look at ordinary characters. As the name suggests, ordinary characters include those commonly used characters, such as uppercase and lowercase alphanumeric characters, and essentially all punctuation marks. Some examples are A, B, C, 1, 5, and so on. Now let's see what are non-printing characters. Non-printing characters refer to sequences formed by escape characters, which express specific meanings. If we are familiar with Linux or other programming languages, we would have seen this before. For example, /n means a new line, /t means a tab, and so on. These are all non-printing characters and all have specific functions. The third category is a special character. Each special character expresses some particular meaning. For example, the $sign matches the ending position of an input string. Two brackets mark the beginning and end of a sub-expression. The asterisk matches the preceding expression 0 or several times, etc. These are what we refer as special characters. The fourth category is quantifier. Quantifiers are used to express or specify how many times a given pattern must appear to satisfy a match. These are 6 types of quantifiers in regular expressions. Let's briefly introduce them. As we have already learned, the asterisk is to match any number of characters. The question mark is to match the preceding sub-expression 0 or 1 time, and in parentheses. N must first be a non-negative integer, means to match exactly n times. We will have some specific examples later, so everyone could get a better understanding. The n and m inside braces means to match at least n times, and at most m times. Let's look at a specific example on the right. For the string app, we require it to appear exactly twice in the target string. The requisite regular expression is written as app in parentheses, followed by a 2 in braces, which means to match app exactly twice. We use the string appapple to test this. We find that a matching pattern indeed exists in the test string, which is app. We now have an idea of how a quantifier can be used. Let's next look at some combinations of regular expressions. Here's the first type, matching a character set as well as its inversion. The expression we wrap in square brackets represents the characters we want to match. For example, ABC. As long as the string to be tested contains the letters ABC, it will be marked as a match. Along the same lines, 0 to 9 means to match all 10 digits. Let's look at another case on the right. Our regular expression is square brackets, AMPL, and the string to be tested is my name is Tom, as long as the string to be tested contains any character in the regular expression. It will be marked as a successful match. Here we just have am, nothing after, and the last am, but it is still a match. Let's look at the inversion of this expression. If we want to match characters other than those in the regular expression, we need to add a caret in front of that expression, which signifies an inversion. For example, the regular expression we are talking about is AMPL, but a caret is added to the front. This will match characters in the test string that are not equal. The matching result then becomes MYNEISTO. And finally, the punctuation mark period. This is how matching a character set using regular expression and its inversion works. The second case is that sometimes we need to match a repeated sub-expression. The main qualifier we use here is the asterisk. For example, ABC in the brackets, followed by an asterisk means that we have to match the sub-expression ABC 0 or several times. Similarly, A brackets B asterisk bracket C asterisk means that we have to match a substring beginning with A, followed by several B's or several C's. Let's look at the example on the right. First, look at a regular expression that matches ABC several times. The string we want to test is ABC, ABD, ABC, ABC. We can see that ABC will be matched in two instances. The first instance of ABC, because the sub-expression appears once, ABD will not be matched. The second match is ABC, ABC, since the sub-expression appears twice and it fits the matching paradigm. Let's take a look at the next example. We start with the character A, followed by any combination of BC. The result then becomes AB will be matched, AC will be matched, and finally ABAC will be matched. This is the result of the match, which illustrates how to match repeated sub-expressions. Let's take a look at another qualifier, which specifies a range of instances to be matched. Previously, we mentioned M, N in curly braces means to match the sub-expression at least M times, at most N times. For example, A curly braces 3, 5 means that a character must appear at least 3 times in a row, and at most 5 times in a row to be included in the matching result. It is worth noting that if M is equal to N, then it signifies matching exactly N occurrences, which is equivalent to N embraces. Let's look at 2 more examples. The first example is GO curly braces 26 GLE, which means the string Google, with at least 2 O's in the middle and at most 6 O's. We'll look at a collection of strings to be tested. We see that the first 3 will be matched, and the last one will not be matched because it has more than 6 consecutive occurrences of O. Look at the example on the right matching exactly 2 consecutive occurrences of O. In this case, for the set of strings to be tested, only the first one will be matched. We've now covered some of the basic concepts of regular expressions. Let's now talk about how to process the date type in Python. First of all, why should we care about processing this kind of data? There are several reasons. The first is that date data is an important type of data utilized by computers. When we write programs and software, we simply cannot bypass them. The second is that within different software systems, as well as manual entry, date data is often not standardized. We know that for computer systems, the lack of standardization will cause many issues. Furthermore, date data can appear in multiple formats depending on time granularity. For example, being accurate to the day or the second or the millisecond, and so on. The fourth is that we often need to perform some conversions between timestamps and a standard human-readable data format, as well as between string and date objects. Often this processing will be more cumbersome and error-prone. Therefore, we generally do not use regular expressions to process date data, but rather employ some built-in third-party standard libraries specific to date processing in Python. They have undergone robust tests and can be used without worrying about errors. There are mainly 3 built-in data processing libraries or modules in Python. One is time, one is calendar, and the other is datetime. We will talk about their functions and some differences later. Let's first look at the time module, which allows us to get the current timestamp. Let's first briefly explain the concept of a timestamp. A timestamp indicates how long a period of time has passed since midnight of January 1st, 1970. It's expressed in the number of seconds as a floating point decimal. Say that we've introduced the time module into the runtime environment. We can now get the current timestamp by calling the time method. The format is printed like this, which is a very long floating point number. This is of course not readable for humans, and you wouldn't know what specific date a timestamp represents. So how do we express a human-readable time in Python? Within Python, there is a concept of a time tuple. Python uses a tuple to assemble 9 time-related elements for normalized time data processing. What do these 9 elements include? They are year, month, day, hour, minute, second, the date of the week, the day of the year, and so on. Let's take a look at how to convert the current timestamp into a time tuple. We use the local time method from the time module to convert a timestamp. After the conversion, we can see from the time tuple, which represents the previous timestamp, that the actual time it expresses is January 31st, 2021. Of course, there are also hours, minutes, seconds, and other elements, but we won't look at them in detail. Let's take a look at how we use some of the methods from the time module to normalize time data. There are 2 ways. The first one is that we use the askTime method. We pass in a time tuple to the askTime method, and it will return the equivalent in the current default time format. For example, this is a time format commonly used in the English-speaking world, January 31st, 2021, in some specific time. The second is that we use the scripttime method, which converts a timestamp into a date in a fixed format, which can be user-defined. For example, we've defined 3 time formats. Here's again the same time tuple corresponding to the timestamp, and we can convert it into the 3 different data formats. For example, it can be expressed as 2021-01-31-19-05-01. Of course, there are other formats as well, as long as a format is provided. It will convert the timestamp into the preset format. We've now covered some of the specific formats for expressing time. We move on to talk about the meaning of fixed symbols in formatted time data. For example, modulo y represents a 2-digit year with the range 00 to 99. %y represents a 4-digit year, %m represents the month, %d represents the date of the month, and so on. You can find out the rest from the slide. Let's now take a look at the datetime module. We've just introduced the time module. It can obtain the current timestamp and convert the timestamp into a time tuple in Python. It contains 9 elements that can be converted into a user-defined data format. So why do we still need the datetime module? Because the datetime module can handle dates as a string. This is something that the time module cannot do. It can convert date data of string type into a fixed format. For example, we define a date string 2021-01-31. Humans have no issues knowing that this is time data, but the computer does not recognize it as a date object. This is where datetime comes in to convert such a string into a date object, which represents one of its core functions. The specific way to do this is that we first pass in a data string and a corresponding time representation format. Using the scripttime method, the data string gets converted into a date object. Here's a specific example. The data string is 2021 January 31st, and its format is %y, which is a 4-digit year representation, plus %m is the month, %d is the day of the month. We can get a date object by calling the datetime.scripttime method and print out this value. We have the same example in the upper right corner, except that the format of the string is different. We again use the same function to make the conversion. We can also convert the data string into a datetime object. Below, we are saying that we can access specific values through attributes of the datetime object. For example, the converted datetime object is represented by format _d. From calling its year attribute, we can find out the year of the date object is 2021. Let's now look at the calendar module, which has its own specific purpose. It is mainly used to process manual and monthly calendars. That is, we get the calendar information for a month or year. Let's first look at how we can get the calendar information for a month. First, we introduce the calendar module and call the method month. We need to pass in a specific month of the year, which here is February 2021, and then we can print out the corresponding calendar information. We can also print out the calendar information for the whole year, here specifically 2021. The latter two parameters represent the calendar display format. If you don't specify a month, it will print out the full 12-month calendar. We can also determine whether the year is a leap year using the isLeap method. For example, 2020 is a leap year, so the result is true. 2021 is not a leap year, so the result is false. So that's some of the simple ways to process calendar data. With that, we have covered all the contents of this lesson. Let's briefly review. First, we explained the concept of a module in Python, the Python programming structure, how to introduce a module, as well as how the Python interpreter searches for and loads modules in a runtime environment. We then talked about object-oriented programming in Python, introduced some basic ideas of object-oriented programming, including core concepts such as classes, objects, instantiation, etc. We also covered the three major characteristics of object-oriented programming: encapsulation, inheritance, and polymorphism. Next, we introduced several concepts of regular expressions in Python, namely wildcards and regular expressions syntax, and the basic character types used in regular expressions, and looked at some examples. Finally, we covered Python's processing of data, mainly through standard processing modules, including time, calendar, and date time. We also talked about timestamps, strings, formatted date objects, and their conversions using some examples. In this lesson, we mainly introduce object-oriented programming, Python regular expressions, and some basic knowledge about time data processing. Now, I start with programming practice. We used to do a code execution with IPython. Here, we will build Python code programs or modules with scripts or Python files. Let me elaborate on the practical operations of Python in terms of object-oriented programming. We first define a class, which is a simple class. What do we see in this class? This module of this class, its name is mysimpleclass.py. We built a Python file like this. In Python, we usually write it. The first line indicates the encoding type of the Python file. For example, define encoding type as coding equals UTF-8. Then we define a class. First, we declare a class using class in double quotes, which is a keyword for Python. Then the class is followed by an ID or the name of a class. We call it mySimpleClass. After defining this class, we need to define some member variables and member methods. As you know, Python's code block structure is expressed by indentation. In the class of mySimpleClass, we need to indent 4 spaces first. Of course, there is no clear rule on how many spaces to indent, but the number of indented spaces must be identical for all the statements in one block. First, we define a member variable, and we write a comment, which is a member variable. A member variable is defined. Assign its value as 100. Then we define a simple method annotation, a simple example function. The definition of this method was mentioned in the previous lesson, in the form of def.self represents a method of the class itself. In this function, or this method, we will execute one line which returns a string, hello Python. Then we've made a simple definition of a class, and the name of it is mySimpleClass. This contains a member variable and a member method, i.e. vary and func. Now how can we generate an object based on this class, or instantiate an object? we can call an initialization method of this class directly. Then we get this object, which is a member variable and a member method. For example, if we want to check the variables of this class, we can print them out. And then we generate the object based on this object to call a method of it. The bracket must be paired. Let's go to executing this Python script and find out what it returns. We use Python 3 to execute such a script. We see that it prints 2 lines. The first row is the value of this member variable as 100. And then after calling this method, it gets a string hello Python printed. In this way, the calling of a class, the instantiation of a class, and the calling of the method after instantiation are all completed. Just now we define a very simple class. Next, we call an actual class. Usually, an actual class contains an initialization method. That is, when we use this class to instantiate an object, it will execute an initialization method. Here we call this class person and define a Python script for this person. Similarly, we indicate that the script's character encoding is UTF-8. Next, we define a class, starting with the class as the keyword, followed by the name person in double quotes. Then indent for 4 spaces. Now we'll define a method of _init_. The method of _init_ will pass in some parameters. For example, the initial parameters as name, gender, age, height, and weight. In this method, we need to assign values to some member variables of several classes of this class. For example, we need to assign values to the member variable of name as the passed-in parameter name. And then what about the parameter of gender? This member variable is assigned to the parameter gender. What about its age? To assign to age, height. The value of this member variable is the height of the parameter passed in. Then the weight is assigned to a parameter like weight. In this case, when we initialize the object of the person class, we need to pass in some parameters to it. And then we define 2 human methods. One is that humans can speak, so we call it speaking, and the method of speaking will pass in parameter, which is the content of what the person says. Then we only perform a simple operation on this method. That is, print the speaking content, or output the speaking content is : in double quotes plus content. Then define a method eating and pass in a list of what he eats. The parameter is foods. So the eating _ foods equals to the incoming foods. The effect of this method is to return the passed-in parameter, return eating _ foods. Next, we need to instantiate this class. For example, we need to instantiate an object called Tom equals person, and this time we need to pass in some corresponding parameters for Tom. The gender is male, his age is 18, his height is 180 centimeters, and his weight is 70 kilograms. At this time, we can call some properties of the object to know the value of some specific properties. For example, we can get its height information through tom.height. Then we can modify the height information to make it equal to 185 centimeters. Then we print tom.height, and we will get the value of 185 centimeters. Now let's run this script to see what kind of output it gets. We see that at the beginning, the Tom object we initialized has a height of 180 centimeters. Then we update its height to 185 centimeters, and it gets a height of 185 centimeters. For example, if we still want to get the name of Tom, we can use tom.name in this way, so that we can get its name. Let's take a look at the result by printing. That is Tom. This is his name. Now let's look at calling its corresponding method through this object.
For example, we need to use a method such as eating. Then this method needs to pass in a parameter, which is foods. First, we define a list of foods, such as bread and apple, which are something Tom likes to eat. Then we call eating. It returns a list of eating underscore foods. That's how we use Tom to call methods like eating. The parameter passed in is foods. Let's have a look at what the return value is for eating underscore foods. Execute. See, the values are bread and apple. In this way, we can understand how to define a class of abstract things in the objective world. Of course, they are human beings, and then call some properties and basic methods of this person. Now let's talk about Python's processing of data. For code demonstration, we still use the IPython environment. Let's enter the environment of IPython and talk about the time module. Such a tool, and then we need to use the time module. We first need to import time. Then we can get a current timestamp. That is how to call the time method through the time module. We'll get a timestamp. The timestamp is such a floating point number when printing out. It shows how many milliseconds passed in for the first year of computer timing to the current time. The timestamp value is not meaningful enough. We can print it by adding some description. For example, print parentheses, quotes, the current timestamp is, %f, quotes, parentheses, to show what the current timestamp is. Then we pass in the text value by passing in a floating point number of the %f. In this way, the printing result is like this. The current timestamp is in double quotes, followed by a timestamp. Let's take a look at the method of local time, which is to pass in a timestamp, and it will transform the timestamp into a special format. We first define a variable such as local time, and then its assignment to obtained by the method of local time of the module of time. Then the parameter passed in by this method is time.time, parentheses, which means a timestamp will be passed in. Now we print and get a tuple of the current time. This tuple of the current time contains a bunch of information. Let's see what they are. We convert this tuple into a string so that we can print it directly. We get a tuple of such time information, which contains several elements. The first is the current year, which is 2021. The month is May, then May 19th. Then the time is 20. The minute is 52, and so on. It also indicates which day it is in a week, etc. That is how we get the tuple of time. It is difficult to understand the specific meaning of the timestamp, but the function of local time can transform it into a readable format. Maybe it is still not good enough. We have a clearer way to specify the date format. The format is implemented by the strength_time function. We define a variable called format_time. Its value will be obtained by the strength_time method of the time module. Then this method has two parameters. The first one is the format which you want to print or want to convert. For example, we use %y dash %m dash %d to indicate year, month, day in hour, minute, second format. What is passed in is actually a tuple of time, the method of calling the local time of time. If it is not designated, it will get a tuple of time of the current timestamp. And then we return this tuple into a readable time format. Let's print this out. And we print format_time directly. We can see the current time is the year 2021, May 19th, 8:55:49 in the evening. In this way, we successfully convert a timestamp into a time tuple and then convert the tuple into a readable time with a specific format. Okay, that is all the coding demonstration of this lesson. Thank you.